Charlie Rich from Nastel Technologies. Welcome to our Tech Talk, Java Memory Leaks 2, Detection to Diagnostics. Today, Albert Mavashev, our CTO, is going to speak about this topic. Some of the things he's going to cover we'll be learning about the differences between the leak detection across single JVMs and multiple JVMs, how to remotely diagnose your JVM memory footprint, and learning about monitoring and diagnosing memory problems in production. Now, as you may know, this is part of a series of Tech Talks we're doing. The series is on Java, alternating with WebSphere MQ. So we have additional topics on both of these coming up. The next Java topic will be on Java garbage collection, CMS versus G1 in Java 7, a real-world comparison. And that's scheduled for, I believe, November 28th. But check the Nastel.com website. These Tech Talks, too, will be recorded and available within a day or so on demand from the Nastel.com website. Albert's going to start his presentation in just a moment, and then we'll open up for Q&A right after that. So at this point, I'm going to turn it over to Albert Mavashev, our CTO. Take it, Albert.
We're going to cover
Welcome to GoToWebinar, web events made easy.
Model for dealing with memory leaks across multiple JVMs. But we're also going to talk about how we actually diagnose these memory leaks once we actually find JVMs that are actually affected. So before we go into the discussion on the detection, I'd like to spend a few minutes and talk about the two perspectives of memory within the JVM. And actually, if you look at the up-and-running Java machine, most of the Java developers and most of the people that talk about memory leaks, they really focus on what's going on within the Java heap. And typically, here we're talking about the maximum or the heap that's allocated, and then the percentage of heap that's actually being used by the JVM. Now, what's interesting is also there's an outside perspective as well, which is the operating system footprint. So you could, for example, on Unix do a PS or on a Windows open a task manager and see what the OS footprint is of the actual JVM. In fact, what you'll find is it's very often the OS footprint and the heap footprint are actually can move independently. So when we're looking at the heap or memory leaks, it's important to look at not just the behavior of the heap, but also behavior of the outside perimeter, what I would call an OS footprint of the JVM. Now, typically, the heap is subject to things like garbage collection, the type of garbage collection used, as well as the GC activity, and that will typically dictate how far heap is actually extended and how much of the heap is actually gets released back into the free pool. Now, it's also important to note that expansion in the OS footprint does not always mean that you have a memory leak. In fact, once the heap is expanded, even though you may reclaim the memory or you may release the memory within the heap, the OS perimeter may actually stay the same. So looking at primarily at OS perimeter is not a good indicator that you may have actually a memory leak, even if you see that OS perimeter expanding. Now, typical when we find people talking about memory leaks, what the first thing they say is, well, why get an out-of-memory exception? And that's typically how people find that there is a leak, or you get things like timeouts, as suddenly the JVM starts to freeze. And that's typically due to the second part, which is increasing GC activity. So that causes the JVM to hang or to block or hold. and soon after you start really getting out-of-memory exceptions. The other symptom, obviously, if you're looking at the heap size, you're going to see a constant increase in the heap size. The not so obvious things that are kind of difficult to look at is things that are happening outside of the JVM. Things like handle leaks, or thread leaks, or class loader leaks. Those are typically are more difficult to troubleshoot. But at the end of the day, if you're leaking memory in the JVM, you're going to find increase in the heap and increase in the GC activity, and then culminating in the hangs or blocks, or and finally out-of-memory errors, out-of-memory exceptions. Now, typical causes, most of the time when we look at leaks, you find several classes. One is obviously things that are going on within the JVM itself, and that's unchecked arrays, unchecked hash maps, or hash map growth, pretty much bugs in the code. For example, developers forgetting to close prepared statements, such as prepared statement sockets or file handles, and not realizing that just by exiting a routine, even though some of the memory may actually get reclaimed, the underlying resources are still intact. Thread leaks and class loader leaks are those typically, especially class loader leaks, are very common within the Java containers or Java J2E containers. You also have leaks that could be caused by bad arguments, such as one listed here, which is disabling class collection. That's especially if you add those in the Java in the J2E containers, could cause leaks. And then the other category, which is a set of leaks that actually bugs within the JVM DLLs or third-party libraries. Now, those would be very difficult to track. I mean, you'll see the JVM growth, but it would be very little you can do about it if it's in their underlying DLLs. That could happen, and then typically you need actually a fix from the JVM vendor. Now, let's look at the detection mechanism. It's obviously, I mean, if you're looking at the JVM and you're constantly looking at the heap utilization, you know that there is a leak. However, it's especially if you're dealing with multiple VMs, farms of VMs that may be on virtual or physical systems. I think a better approach is actually use a heuristic model. And an example here, it's if you're looking at the chart pattern of heap, you're going to see kind of this sloping chart, right? So the heap utilization is constantly growing versus something that's fairly constant. Now, the reason why charts are kind of erratic a little bit is because of garbage collection, right? Heap is getting consumed, and then once the collection kicks in, you have release of all of the memory that should be released by the garbage collection. So what you have here is a pattern of growth, and obviously if you're constantly watching JVMs, you will detect it and say, hey, this is an abnormal growth of resources. Versus here, the second pattern is fairly constant, where it fluctuates around a fairly constant trend line. So we have a rising trend line where we have typically a resource accumulation, and you have a fairly constant trend line down below. Now, if you actually break that down, what you'll find is that a chart pattern of a VM, or in fact of any, it could be operating system of VM, that's actually accumulating resource, you will find a pattern of accumulation. And the pattern of accumulation is typically going to follow by memory allocations, and then followed by deallocations, which is typically caused by GC activity. But what you'd find is, if you have a memory leak, you'll find constant, what we call higher highs in the peaks, and then higher lows at the bottom. That typically tells us that the phase of accumulation and the phase of deallocations are not actually equal. And it constantly leaves a slack, which is the memory that's actually being retained by the underlying VM. So that chart pattern really means that we have a resource leak or a JVM that's constantly accumulating resources but is not releasing those resources. Now, you can apply the same concept to memory, handles, threads, pretty much anything that you can consume or a process that can consume. So if you see that pattern, and obviously we're going to go into the details of how we do that automatically, there's a high probability that you have a resource leak. Now, it is possible that application is designed in such a way that it's actually part of the application design, where you load stuff from a database, let's say, you populate hash maps, and you keep some of that retained storage in memory. Now, in that case, the only solution, obviously, is to bump the heap size, or you have to think about re-architecting the application. But in general, what that means is essentially, regardless whether it's intended or not, that you're going to hit that ceiling at the top, and then the JVM is going to roll over. Now, let's look at the other chart pattern that's interesting. That's where you have a higher highs, but GC activity brings it right back to the steady low. So the lows are not going higher, but we see higher highs. Now, in this case, I would qualify it as not a leak. It's more of a behavior of the JVM that's processing more workload, but the GC activity brings it right back into the steady state. Now, in that case, it is possible you could still blow out the heap, maximum heap size, but I wouldn't qualify it as a leaking behavior. So the idea here is actually to look at this and say, well, can we do this programmatically and automatically across multiple VMs, right? We don't want people to sit and look at these charts and try to analyze them, by hand. So what we want to do is being able to look at the multiple VMs. It could be obviously in production and in QA environments, right? And apply this model of analyzing chart patterns automatically across multiple VMs, and basically looking at things that we want to monitor, such as memory, footprint, handles, threads, anything that could potentially, or any resource that is a finite resource that is important to the performance of an application of VM. Now, in the case of JVM, we want to look at things like how much heap is allocated, how much is unused. We want to look at GC activity, frequency, and duration. And for each of the metric, and that's kind of, think of it as almost like a pseudocode, right? For each resource that we pick, or combination of resources, we want to measure advances and declines. So actually, if we're looking at the chart pattern here, what we want to do is actually looking at the rate of advance and the rate of decline. But we also want to see what is the ratio of advances and declines. And that should be able to tell us whether we are, in fact, leaking a specific resource, such as memory. Now, for this case, what we do is we measure what we call a momentum. And momentum oscillators are actually used in many different areas, especially in, for example, trading and technical chart analysis when analyzing stocks. But it's the same concept where it measures the rate of advances versus declines and comes up with an index. And we can look at resource leaks in terms of its momentum oscillators. Now, the question here becomes is, can we, one can say, well, can we really detect the memory leak by just setting a threshold? Well, you could set up a threshold of, let's say, 90%, but then you could have a lot of false positives. For example, you could have a VM that is constantly goes up to 90% and then goes down to 40%. You will be constantly getting false positives, false notifications. So we don't think that setting a specific threshold is necessarily a good idea to detect leaks. It can give you a good idea that if you want to say, hey, we're getting dangerously close to the limits of VM, but it doesn't really tell you that you have a leaking type behavior. So we want to do is looking at these indicators, we want to measure momentum oscillators and then decide what's going on and decide whether we have a leak. Now, getting a little closer to and actually expand the momentum oscillator, what you find is momentum oscillator actually goes from 0 to 100. 0 means that we have all the declines, meaning from the moment that we start to measure, and typically it's measured over a number of samples, that we've only seen declines. That typically doesn't happen in VM, so you can't deallocate memory that you haven't allocated. So what you typically have is advances and then declines. If you are at a steady state, which is where advances are the same as the declines, you would typically be at a 50. So any momentum oscillator that typically hovers around 50 means that there is no, think of it as there's no leak, or the advances do not outpace declines, and in fact they are almost equal to one another. So you want to hover about around 50. As we start going above 50, that's where we start really looking at the danger of a memory leak. And obviously in 100, we're talking about all of the samples that we've seen so far have been advances and not a single decline. So it really measures supply and demand dynamics for a specific resource. I think that's an important aspect, and it goes from 0 to 100. It doesn't really say it's 100%. So you could be, for example, at 90% heap utilization and still have a momentum oscillator of 50. Now, go a little further, creating a combined index for a set of VMs. Now, in this case, we're calculating a momentum oscillator for each VM, and then we're creating a composite index, a composite oscillator that's computed off other oscillators for each VM. Now, in this case, again, we're using an automated kind of process where a momentum oscillator is computed automatically for each of the VMs. Then we compute a composite oscillator that now takes into consideration other oscillators. So you have multiple oscillators leading into this composite oscillator. So it's a good way to have almost like, think of it as a dashboard of multiple oscillators that tell us what is the risk of one of the VMs, in fact, leaking memory. And the composite index telling us what is the farm of VMs is actually doing. Now, typically, in this case, and I want to show a little bit of math here. It's not really complicated. You have the oscillators could be computed fairly easily by computing exponentially moving average of gains over X number of intervals divided by the exponential moving average of declines. So if you measure, just take samples of heap sizes or garbage collection, and then you compute the exponential moving average, divide one by the other, and you get your oscillator. So you can also have a simpler formula where you get a simple moving average of gains divided by the simple moving average of declines. So it's a fairly simple formula, and it could be used automatically, and you could use it automatically to apply to different resources and detect whether you in fact have a leak of a finite resource, such as heap, memory, or anything else. Now, typically in the workflow, what we find is, okay, so now that you detect it, what do you do about it? And what we've done here is, and we actually make it available online for free download, is an analysis tool, a diagnostic tool. So once that you know that a specific VM might be leaking, what do you do next? Now, typically in the pharma VM, one of the things you can do is isolate that VM, take it offline, maybe fail over to a healthy virtual machine. But in the meantime, you don't want to shut this thing down. Why? Because you want to maintain where it is so that you can do some diagnostics. Now, typically, diagnostics requires that you've actually connected the VM and actually analyze the heap. Now, in typical environments, if you're running that VM on any platform, what you have to typically do is take a heap dump, then transfer it over It typically gets to be a big file, and depending on the size of the VM, it could be in gigabytes, and then run through some kind of a diagnostic tool. So what we've done here is we've actually embedded the agent in the VM that kind of sits dormant without impacting VM at all. And we are just looking at the pattern of behavior of each individual VM and say, okay, this VM is, for example, leaking. It's got 80% memory utilization, and the oscillator could be, let's say above 60. So we may want to look at this VM. So in the meantime, we can fail over to a healthy virtual machine isolated, and then have our developers and people who understand application to actually connect remotely to the VM and do the heap diagnostics. Now, in that case, what do we actually see? And then we'll see a good example of that live, is that once you open the VM, it's basically you have to actually analyze all of the objects and compute the trees, allocation trees, and see exactly where memory is being used. So what I'd like to do now is go to the actual tool where I'll show some of the examples of the diagnostics. So let me minimize this. So what I'm going to that's running, and it's running on my laptop, and it's running on this port. So what I'm doing is, if it was, let's say, in a remote VM, I would just put a host name. So let's connect to that. Let's connect to that VM. And what we typically get by connecting is we get kind of a summary information: number of classes loaded, number of threads running, available processors, maximum heap size allocations, and total heap memory and heap use. Down below, we know we're, for example, at 22%. But we may still be experiencing, for example, even though we might be running still at 22%, our oscillator could actually be saying that we are leaking memory. So what we want to do is take a heap dump. So what we're doing right now is we're actually connecting remotely to the VM, and we're analyzing the heap as the VM is running and figuring out where is actually memory is used. Now that could take a few seconds. What we're actually doing is the agent walks the heap, creates a tree of allocation tree, and then sends it back to the client. So as we see, we're processing heap references. We're going to be recomputing sizes, and then we're going to actually present that on the UI. So that's where we compute retained sizes of objects in memory, and we're going to show that in the list. So typically what you'd find here is, number one is we have instance counts, we have total bytes. We have also the average size, so we average size per instance. And what's typically interesting is in the first, typically when you try to troubleshoot memory leaks, you're going to find that some of the top objects are going to be typically primitive objects, which are fairly difficult to troubleshoot because there could be bytes or integers or doubles. So what we typically do is we can look at, for example, hash map entry, which tells us that a lot of the objects are actually maintained in memory in the hash maps. So what a good thing would be just to click on the object, and it will tell us right up front here the top 10 by retained size. So without really going any further, it tells us that out of the memory that we're using, 479 megabytes, which seems to be an area where we are kind of allocating memory. That's where most of the memory is actually being used. And what's good about this is it tells me if 479 megabytes is used in this specific data structure, but it also tells me what are the different makeups of that 479 meg. So we see 68, 68, 68. So we see a bunch of different hash maps here that are actually using a lot of different memory. And if we look at the references to, we only find one reference. So we know that this hash map is only referenced by this object. So if this object were to get deallocated, or let's say we lose reference to this, this would get also garbage collected as well. Now, as part of the diagnostics, this allows us to tell us what is the retained size, which is typically tells us that if we were to deallocate this this hash map, 68 megabytes would be released. We're also looking at where is it actually defined. So from a diagnostic standpoint, and using this tool specifically, we can very quickly determine where memory leaks or where most of the memory is actually being consumed. Now, in the history, this is where, as the JVM running, we can take multiple snapshots. And then we can actually compare. It doesn't have to be 2 snapshots. You could take 5 or 6 or 10 different snapshots. And then we can compare exactly where the growth is. So if you're running in the VM and you're not sure exactly, where a different, where memory allocation is actually taking place, you could take one snapshot, and then you could take multiple snapshots while it's actually running, and then compare where the growth is. But let's take us let's take the second snapshot, and let's see what it actually will show us. So okay, it's still loading. Okay, so we have different, and here we actually sort by largest absolute change, which is the change in the number of bytes. We can also look at the percent change and then apply that. So we know that, for example, following data structures are actually moved up in percentage-wise. But if you look at the largest absolute change or largest value, you could also sort by that, or largest absolute change by total size or by instance, in this case. Then we find that we have this, we have strings basically that are growing in sizes. We can also look at some of our objects here, Nastel.com objects that are actually going and exploding in the number of instances. So we go and look at the top instances. And then we see that where this object is actually, it's 17,000 bytes, and then we see the actual footprint of this 17,000 bytes. So we know exactly which one of those fields is actually uses up the 17K. So it's a good way to understand where the memory is used. It's also a good way to understand how and where to optimize. And obviously, developers then can take a look at it and say, okay, well, this looks right, or this looks wrong, or we need to optimize. This really shouldn't take that much, space. Or why are we, why is it that if we look at, for example, the top instances of hash map, why is it that we're using so much in these maps, and that potentially may need to revise the code or fix the code. So the concept here is really kind of facilitating the workflow of going from detection to diagnostics, because both of them kind of go hand in hand. If I know there's a problem, I need to be able to get to the root cause of the problem. And so looking at this, for example, chart pattern. Now, if I now detect and know which JVM is actually offensive, it has a problem, do I have the right tooling that I can actually connect and diagnose the problem quickly, so I can get back to my developers or developers to look at it and actually fix the problem. Now, with that, I'd like to conclude. If you have any questions or suggestions, please send us an email. You can also visit us at www.nastel.com. You can also visit us on Facebook and LinkedIn. We are also reachable, obviously, by phone. Some of the tooling that I talked about, such as Heap Detective, is available online for download. It's actually a free tool. And the detection mechanism is something that we actually provide within our products as an automated process. Thank you.
Thank you very much, Albert. That was very insightful. So we're going to open up the floor for questions. So please get your questions, put them in the question box, and we'll answer them as we go. So the first question I have is the presentation file going to be distributed to the participants' emails? And the way we're going to handle that is this is being recorded, and it'll be a video on our website, an MP4, and you'll be able to click on that on our website and do a replay. So hopefully that'll help everyone, and that should be done within a day or two. Again, I want to remind everyone that this is part of a series of Tech Talks on both Java and alternately on Webster MQ. Our next Java session, since this is a Java audience, is, as I said earlier, on Java garbage collection, CMS versus G1 in Java 7, real-world comparison. And please join us for that on November 28th at 11 o'clock. All right, questions, folks? All right. Albert, I have your first question there. The first one we have is, how do you distinguish normal application loading in a JVM versus a memory leak? Albert?
Yes. Well, as I mentioned in one of my slides, what we're trying to determine is resource accumulation. Now, typically, it happens because of, very often it happens because of a memory leak or some kind of a leak. But it is possible that a normal application could be designed in such a way that it accumulates resources. Whatever the reason is, the outcome would be fairly basically the same, meaning at some point you will run out of resources, right, whether it's designed or intentional or not. And what we're trying to do is detect that pattern and allow you to then give you a chance to troubleshoot and figure out why this is occurring. And whether the outcome could be, okay, we got to bump the heap size, or we got to look at re-architect the application because eventually it'll lead to JVM basically falling over. So we call it a leak, but in a sense, if you look at it, it's basically resource accumulation caused by intentional or unintentional, what I would call bugs in the applications themselves.
Thank you, Albert. Other questions, folks? Okay, I see another one there. Can the techniques, Albert, that you've described during your session here, can they be used for other metrics beyond memory? Al?
Yeah, the technique of analyzing technical charts, usually what we do is we apply it to resources that have a finite amount, such as memory, storage, anything that has a finite amount of things that you can take or you can allocate or deallocate. So yes, it could be used to determine direction or to determine if you're running out of resources. Again, we apply specifically for resources. One thing to remember is it's really about supply and demand of a particular resource. And what we're trying to measure here is the rate of accumulation and then the rate of deallocation of a particular resource. So you can apply it pretty much to anything that is important, mission critical, but also has a finite number of things that are claimed or deallocated by applications. So things like operating system resources, threads, handles, storage, CPU, memory.
All right. We have another question in the queue here. Enjoyed your presentation very much and very interesting information you provided. But I'd like to know, how is the heap analysis that you spoke about different from the default tools that can come along with the JVM? Al?
Well, one of the basic difference is the fact that you can connect remotely to the VM without having to go and to sign on to the machine and actually generating heap dumps, which could be time-consuming. And then obviously you need to have the tooling to analyze gigabytes and gigabytes of data and figuring out, what's going on with the heap. So one of the convenient things is that you can just connect to the VM and analyze the VM as it's actually running. Now, because the agent is actually outside of the VM, it's not running as part of the JVM heap size, you can analyze heap even though your VM could be completely out of memory. And you wouldn't be able to do it if you were just running actually within the VM itself. So we can look at a VM that's completely at 100% utilization, where not a single application can actually do anything, and we can tell you remotely what's going on with the application or the application server. So that would be the primary differences. The other thing is also the way we compute some of the retained sizes, that we can show you exactly where you need to focus your attention versus just to tell you here's all the objects and here's where, what the sizes are.
All right, more questions, folks? Looks like we have another one popped up here. All right, everything in this world has a cost. What's yours? What's the overhead incurred by your agent running within the JVM? Albert?
Well, the cost is, while the JVM is running, the agent is pretty much dormant. The cost is really when you're trying to analyze the VM. Now, when we are running outside, because we're running outside of the VM, we actually would pause the VM while we're doing a heap analysis. Now, somebody would say, well, that's a hit, but essentially, you're doing that at a point where JVM is pretty much useless to begin with, where you run out of memory or there's a problem of some sort, or applications already experiencing a significant degradation due to garbage collection pauses. So the agent is pretty much dormant while application server is running. Once we detect there is a problem, then the only recourse really is to analyze the heap size. And at that time, you typically want to take it offline, fail over to another box, so there's no impact to the end users, or there's no impact to the traffic. And then you want to be able to have the tools to come in and look at the problem while it's happening, so that the developers have a chance to actually fix the problem.
Any other questions? Going once, twice, 3 times. All right, well, I wanted to thank everyone for attending the session. I hope you found it very helpful. Thank you for your questions. Thank you, Albert, for the insightful presentation. And this will be available on our website within a couple of days as an on-demand video. And also want to offer to you folks that we have our free Autopilot Heap Detective for leak detection, and you can download that from the Nastel.com website. And please do, and please let us know your experiences with that. And come back, same time, same station, for the next in our series of Tech Talks on the following week. Check the Nastel.com website for the details. Thanks, everyone.